Hey everybody, today we're going to be blocking the event loop and then we're going to be unblocking the event loop, and I'll show you why you don't want to block it, and I'll show you a couple of ways to avoid blocking it. So I'll show you a way you're probably familiar with using some Node built-in functions, and then a couple ways you might not be familiar with using worker threads and forked processes. So the first thing I'll walk through is why this is bad. So we have a server running here, we have a ping endpoint. And this is just a request and response. It's coming back right away in 4 milliseconds, 3 milliseconds. And then we have this sync write endpoint. And when we hit this, it's going to write a file to disk. It's going to write a really big file. And it's going to take almost a second. And if we fire off concurrent requests, it's going to take a second for each of those requests. And they will run in sequence. So this whole thing takes, 3,600 milliseconds because these individual requests are happening one after another and not in parallel. And then if I call this endpoint again, it will not only will it run these in sequence, it will block any other endpoint. So this is why blocking the event loop is bad, because this ping also has to wait for the sync write to finish what it's doing before it can handle any requests. So you want to avoid that. You want to keep your main thread and your main event loop clear. You want to process things as quickly as possible so that you can handle more requests. So the first thing we'll look at is something you're probably familiar with. So this write file sync. So what we're doing here is we're writing a file, and I'm also doing some logging. That's all these perf methods are doing. It's just doing some logging. So we're going to write the word hello 50 million times to a file, and we're using write file sync. And so if you've ever used Node before, if you've ever used any of the sync or async functions, you'll know that there's an async version of this. So we can just turn this into a promise, or we can use callback, but I'll use a promise here. And we will change this to be async. We need to import the promise version of this function. And now this will run asynchronously. So what that means is it will when it accepts the request, it's gonna write the file to disk in a non-blocking way. I'm going to change my front end and just have this be hitting async write instead. I'm not going to walk through the front end code. It's pretty simple, and you can take a look at it on the repo if you want. I'll link that in the description. I'm also going to link a couple of videos in the description about how the event loop works if you want to know more about that. So now we have this asynchronous version, and if we fire off a request here, it's going to take 1200 milliseconds. If we fire off 3 concurrent requests, we'll see they fire off almost in parallel, and when they come back, they all finish at the same time. And we can see the longest one took 4,800 milliseconds, and the whole round trip took 4,800 milliseconds. So they're all happening in parallel, which is exactly what we want. Also, importantly, it frees up the ping endpoint. So if we ping in the middle of this, it will be unblocked while this is working, while this is writing to disk, and we can see that happening. That ping is coming back really quickly. So that's write file sync and write file. Nothing earth-shattering here, but let's do something a little bit more interesting. So next I'm going to do a synchronous loop function. So we're just going to have instead of writing this to disk, we're going to have a loop. Okay, so now we have this loop function, and it's just going to sit here and count to 1 billion, and that's going to block the main thread too, because this is a synchronous operation. It'll get to this loop, and it won't be able to move on until it's counted to 1 billion. So that's going to take a little while. Let's go back to our front end. We're not using write file anymore. Go back to our front end, and we will change this to be sync loop. And if we go try this, we'll see it's gonna do kind of the same thing. It's taking about a second. If we run it a couple times firing off this request in parallel, it's gonna run in sequence. So that whole thing took 3,500 milliseconds. It's also going to block the other endpoints. So this is like blocking the event loop, and we don't want to do this. But how do we get around this? So like, could we just wrap this in a promise, like the write file, write file sync to write file? Let's try that. Okay, so now we are doing this inside a promise. We've wrapped this in a promise. Do we think this will work? I'm going to try this again, four at a time. And yeah, we see the same thing. So that really didn't do anything. The ping just, it looked like it didn't take as long, but the ping is still, it's just because I'm clicking it a little bit later than this sync loop button, but the ping is taking still, it has to wait for all these requests to finish before it finishes. So yeah, so wrapping in a promise really doesn't do anything. And the reason for that is because promises aren't magic. They don't like magically unblock the event loop. What they do is they just defer something until the next tick of the event loop. And so when it gets to that tick, it will pop this task off of the event queue, and it will run this task. But like, it's still got to run this task synchronously on the main thread. So how do we get around this? One of the ways, so there's two ways we can do this. Well, there's probably more than two, but I'll cover two. We can either use a forked process or a worker thread. So the first one I'll cover is a worker thread. And I'm gonna cut this, and I'll say I'll add a worker. Okay, so I've added a worker. I have to import this worker. The worker, the first argument to the worker constructor is a file. So we're gonna send this to worker.js. And I've got that over in, next to this file. And the other thing is I'm going to show you how to pass data into a worker. So we have this worker data. And let's get worker and worker data from the worker thread module. Okay, so that's good. I would also, if this were a production app, I would handle errors and things like that, but we're going to keep it simple for now. Worker, move over here. And so I'm going to paste my loop in here, and we will, when this is done, we're going to actually need to import a couple things from worker thread here. Okay, so we've imported parent port and worker data. And so this is how we pass data here. So we can say worker data. If we go back to our other function, actually we'll go back there in 1 second and we'll pass that data in. No, I'll do that right now actually. So if we go back over to worker data, if we go back over to our app, worker data is going to be the number of times we want to loop. Okay. So back in our worker thread, we are going to, when we're done with this, we will post a message to the parent port. So we'll post the count back to the parent. And so now, if we go back to our app, we can, let's call this async worker. And we'll go back to our front end. We'll call this async worker. Okay, and if we save that and refresh this, we'll send a request. So it's still taking a second. You can't really stop it from taking as long as it takes. But if we fire off a request, we can see they're all firing off in parallel, and they're all coming back in parallel. So we have everyone is taking around 900 milliseconds, and the whole loop takes around 900 milliseconds. This also keeps the ping endpoint open. So so putting things onto, using a worker thread to get this synchronous work off the main thread is one way of unblocking the event loop. The other way, or another way, is using a forked process. And I'll talk a little bit about the difference. I won't go too deep into it because for this use case, there's not much of a difference. The difference between a worker and a forked process is that a forked process gets its own memory space, and it's also a little bit heavier weight. It requires a little bit more resources, but But in this case, we're not sharing memory anyway in the worker, so there's not too much of a difference. One of the things that we will want to watch out for, though, is like you wouldn't really want to do this. You wouldn't want to spin up a new worker in an endpoint like this on each request. You would probably want to use something called a worker pool so that you can set a limit on how many workers you would want to spin up. And if you do that, then it will, say you have a limit of 8. If you have 8 cores on your computer, you can set a limit of 8 workers. And that way it's not going to like use too many resources. You run the risk of using too many resources. So that's a little bit about workers. Let's take a look at forked process. So it's kind of the same, similar API. We'll use forked process. And we get that from the child process module. And let's see, so we have a fork. We're going to have fork on message and count. We're going to stop perf. So this is all basically the same. We're also going to need to send a message to kick this off. Forked. Oh, it should be forked on forked. Send, and we'll send that 1 billion. So that'll kick it off. And then we want to send this to fork instead of worker. And I'm going to call this async fork. Okay, so now we are going to go over to fork.js, and I'm actually going to grab this loop from worker. Fork.js, and we don't need to import anything here. We're just going to say process.onMessage. So this is the process here. Now this is the child process of the parent that we just forked from, and so we're going to send this message. We're going to send the number as a message. We'll call this num. And when this is done, we are going to send a message back. And we'll exit the process. Okay, so now if I got this right, this should do something very similar. So if we send this to async fork, great. So we're seeing elapsed time is 900 milliseconds, so it's taking about a second again. And if we fire off 4 in parallel, we can see that they're all firing off in parallel. We can also see, if we go back to our fork, we can see what the process ID is. Okay, so we're logging out the process ID. So we can see this is each one of these messages is being handled on a different process. And so this is actually kind of the same thing as workers. Like, you don't really want to just create a new process every time you get a request. So next, I'm going to show you how you can avoid that with the cluster module. I'm not going to show you worker pools, but I will show you the cluster module. So but let's just pause here, and I will note that that we've now seen a couple of different ways that we can run this synchronous process, this counting to 1 billion, off of the without blocking the event loop. So that's great. This is running in parallel. We can ping, the pings go through. So this is what you want. Okay, so the last thing I'm going to show you is cluster. So I have actually cluster set up in a separate app. And so if we look at this, and I'm actually going to stop this. I'm gonna kick off the cluster, because it's actually a totally different file. And the reason for that is because with the cluster module, instead of kicking off a new process with every request, you're actually pre-allocating these processes, or not allocating, but forking processes, and it's based on the number of CPUs that you have. So rather than at request time, it's at app instantiation time. So we're gonna import the cluster module, and this is going to look a little bit different. So cluster gives us this is master property, and so we can check if it's the master, we'll do one thing, and if it's not, we'll do another thing, because that means we're in a fork. So if we're in the fork, we're going to start the app. We're going to start the Express app. If we're not, we're going to create a fork. So that's what we do. If we're in the master process, we will create a fork. And we're going to use our CPU, our number of cores to do this. So I'll say num cores is OS. So we're going to need to import the OS. CPU's length. Okay, so we have our number of cores, and I'll say so for each of our cores, we're going to call cluster.fork. And that will do this. That's basically creating a forked process, and that's going to be our else condition. The other thing I'm going to do, I'm going to log out the process ID of the master process here. And I'm going to do the same thing down in each of the forks, so we can see that that's going to be different. And actually, we can already see it. It's already doing what we want. Let me call this master, and we can see right here, master process is 14.871, and then we have 73, 74, 75. So like this is already forking these, and it's doing it based on the number of cores. I'll show you what happens in a minute. What happens if we have more requests than the number of cores? But for now, yeah, this is for let I, yeah, and then we can just a little bit of like resilience. We can say if the process exits, we'll create a new fork. Okay, so let's see. So we already see we have a whole bunch of processes running, and if we hit this async cluster button over here, we see that it takes a second. So it's doing the same thing. It's counting to 1 billion, and it's doing it synchronously. And so this is basically the same idea as what we just saw, where we were creating a new process on every request, except we're creating a new process for each core when we start up the app. And so same thing, we see the pings go through. It's just like the previous thing we did. The last thing I'll show you here is what happens when we have more requests than the number of cores. So let's say we have 16 requests, because we can see this is starting up eight processes. So if we have 16, twice as many as the number of processes, it's going to, or we're going to see 2 batches. So it handles 1 batch, and then when those start finishing, it's going to handle the second batch. And then those all finish, they all take about the same amount of time, except it takes twice as long because it's doing it in 2 batches. What we see is that this ping actually goes through in between the batches. So that's nice. That's kind of, that's a benefit of doing it like this. But the reason for that is because you can only do synchronous work on a free CPU. So this is CPU bound work, and it's different from, say, a network request. That is a totally different situation because it's not CPU bound. And so if you're ever doing anything like writing to disk or using the Node crypto module or doing something like this where you have to do a lot of heavy computation, you are bound to the CPU. And so you need to, you kind of need to take that into account. So that's about it. I hope you learned something today. And again, I'm going to leave those links in the description. And if you have any questions or comments, I'd love to hear them. Just post it in the comments. All right, I'll see you next time.